Hey class, Mr. Mohidian here with a video regarding special right triangles. We've investigated this topic a bit, but we're going to revisit it and also extend some of the concepts we've developed. So here's a bit of a review question. The question is, what is the perimeter of this square given that its diagonal length is 10? Well, recall that we have what's called a 45-45-90 triangle, and the rule of thumb for that is that if these lengths are the same, which they would be if these are both 45 degrees, and this is 90, then this length here we consider as that same length times the root of 2. So the length that we're given, this 10, corresponds to this root of 2. Now you may wonder, well, how do we know these are 45 and 90? We'll recall that a square, of course, has definition 4 right angles and also 4 congruent sides, which means that it's a rhombus, and a rhombus's diagonals bisect the angle, so this must therefore be 45 and 45 as well. So the 10 that we're given corresponds to a times the root of 2 in terms of the diagonal, the length, the hypotenuse of the right triangle. So in a sense, we could say that 10 is sort of equal to a root 2 if we're trying to scale together this shape and the original shape. So quickly you can see that the actual side length A would just be 10 over the root of 2. Which for most cases is okay, but you've learned last year during Algebra 1 that there's actually a way to write this in a bit more familiar form. So I'm going to write 10 over the root of 2, and I'm going to simplify it a bit, and I'm going to multiply by the root of 2 over itself. You may wonder, well, how am I allowed to do that, or why should I do that? Well, notice, this is a number, and this is that same number, and they're dividing each other. Or rather, this is dividing that number. So really, keep in mind, this is just the number 1. Anything divided by itself is just 1. And multiplying by 1, moreover, doesn't change anything. It's the identity. It remains the same number. So both before and after this multiplication, I'm still going to have the same value. The reason that you can do this is, or the reason that it's useful to do this is the following. On the top, I have 10 times the root of 2. And on the bottom, I have root of 2 times root of 2, which is root of 4. Well, wait a second. Root of 4, the square root of 4 is just 2, isn't it? Because, of course, 2 times 2 is 4. So furthermore, I can simplify this to be 10 times the root of 2 over 2, but 10 over 2, of course, is just 5. So we have really 5 on the root of 2. Now let me at least convince you that these are the same numbers. What I'm claiming is that this number, which we got just by 10 divided by the root of 2, I'm saying that's actually equal to 5 square root of 2, which, since this is a square, this is also 5 square root of 2 in terms of these side lengths. Well, let me convince you that these two numbers are indeed the same. So let's see my calculator here. 10 divided by the square root of 2 is approximately that number. And 5 times the square root of 2 is the same number. So these are indeed the same. So returning to the original question, what is the perimeter? Well, if one side length is this, then a square has all 4 sides the same. So this plus this plus this plus this is just the same as multiplying by 4, which gives me 20. 5 times 4 is 20 on the square root of 2. So this is taking what we've already learned about 45, 45, 90 and going a bit deeper. Which brings us to our next topic, which is another special right triangle. So the square is, of course, a classical shape, a regular shape. Let's also look at a classical triangle, a regular triangle, which is to say an equilateral triangle. So we're going to develop this idea called the 30-60-90 right triangle, and it comes from an equilateral triangle. So recall that in an equilateral triangle, you have 3 equal sides, and sort of as a consequence, you could say that all 3 angles are also equal. So it's also equiangular, you might say. Well, all triangles have 180 degrees contained within them, and since all 3 of these angles are the same, it therefore follows that all 3 of these are 60 degrees. In fact, our warm-up on Monday worked us through this particular scenario. So what I'm going to do is I'm going to call all 3 of these side lengths an unknown length called 2x. You might wonder, why am I calling it 2x? Why not just plain old x? We'll get to that in just a moment. So all 3 lengths are 2 times some number. What I'm going to do is I'm going to create what's called an altitude. So I'm not doing it exactly super accurately, but just for a rule of thumb, this is sort of the height of the triangle. In fact, I'm going to call it h for that reason. So this is by definition an altitude. We've proven in the past that an altitude in an isosceles triangle, which an equilateral is a type of, creates two congruent triangles. You may want to check that for yourself. You'll notice that these angles are both 90. We have this length being the same as itself, and of course these being the same already. So by HL, they're congruent, which means that if this was 60 together, then this is now 30 and 30. You can still see they all make 180 together. And also, an altitude counts as a perpendicular bisector. We've also proven this in the past. So what that also means is that this length right here is x, and this length right here is x. So we've done a lot right there from the original triangle. All I've basically done, though, if the numbers are distracting you, is take a regular equilateral triangle and drop this line, and it creates a new segment which is half as long as it used to be. So 2x becomes just plain old x. We call this height. So I'm going to get this a quick little sketch to simplify some of the clutter. So if I were to just take this shape and look at it in isolation, what I have is I have 60, I have 90, and I have 30. I have the hypotenuse here is 2x. I have this length here is now just x. And I have this pesky h. The reason it's pesky, I would say, is because the other ones are in terms of x, but that's in terms of h, which is not x. And that means I have to have twice as much information. I've got to have two variables. Well, we know a relationship with these three pieces, and that's that the one leg squared plus the other leg squared is equal to the hypotenuse squared, or the Pythagorean theorem. So in general, that says that a squared plus b squared is equal to c squared, where c is the hypotenuse. Specifically in this shape, that means that x squared, which is I'm going to call as a, and the other leg squared, I'm going to call h, is equal to the hypotenuse, which is 2x squared. Now, notice the parentheses there. I'm squaring the entire hypotenuse. That's going to be important. Well, let's see. X squared is just x squared. I can't really simplify the left-hand side. However, the right-hand side, 2x, remember, this really means, sort of in your thought cloud here, what does this mean? This means 2x times itself. 2 times 2 is 4, and x times x is x squared. Okay, now we're getting somewhere. I'm going to gather my x squared terms together by using the rules of algebra. H squared is equal to, let's see, 4x squared, take away 1x squared. Well, 4 take away 1 is just 3. X squared. I almost have h all by itself. I just got to get rid of the squared, which we know by now is to take the square root. So those will cancel, giving me just h on the left-hand side. Well, recall that this is the same as the square root of 3 times the square root of x squared. Well, the square root of x squared for the same reason is just x. Long story short, you can take this square out, and that'll give you x times the root of 3. So now we have a new way to express this length. This is a value. This is twice as of that value, and this other leg is that same value times the square root of 3. So I'm going to connect it back to the original A letter that we used with the 45, 45, 90, just so you see a little bit of consistency here. So from this Pythagorean model, what we've arrived at is the following. This is sort of the key picture to keep in your mind. I'm going to change the orientation some just so you don't get used to the same picture every time. Oops, scroll up a bit. So that's 90. The smaller of these two angles would be 30. Remember, across from the smaller of the two sides. And the bigger angle across from the bigger of the two sides. The shortest length, which is across from 30, is a certain length. We'll call that A. The hypotenuse is twice as long, as we saw earlier. And the medium-sized leg, the leg across from 60, is that same length times the root of 3. So one way to remember this pattern, kind of a gimmick, but it does help sometimes, is to notice you have 1a, essentially, really, this is just a 1. 1a, 2a, and root 3a. So it's sort of like 1, 2, 3, but with the square root there. So let's get a quick concrete example, keeping this picture sort of in the back of our head in terms of this is the model, just like 45, 45, 90 was this model up here. Let's take a look at a specific shape. Trying to get these all on the same screen. Okay, so here we have a shape, and we fill in some of the lengths here. Let me say that this is 60, 90, and let's say this is 12 units in length. And the question is, what are the three sides, or the other two sides, rather? Well, keep in mind that all triangles having 180 allows us to determine that this is 30 degrees, obviously. Well, compared to the original model, right? Let's just zoom out, fix this. Compared to the original model, 12 is the hypotenuse in our particular shape, and in the original shape, 2A is the hypotenuse. So if you were to sort of reorient these, you'd see that relationship. So if 12 is 2A, then it simply follows, of course, that divide both sides by 2, 6 is A, which means that the shortest length would just be half as long across from 30, and the medium-sized leg would be A times the root of 3, or in this case, 6 times the root of 3. So without using any kind of trigonometry, without using any kind of Pythagorean theorem again, if you can recognize this model, which is again half of an equilateral triangle, then you can sort of save yourself a lot of work and immediately find these values. Now, since we've learned a bit of trigonometry, what you can notice is that you can actually, these are actually verifiable by using trigonometry. What I mean by that is, for example, 30 degrees, from there you have opposite 6 and hypotenuse 12, which means that sine of 30 would be 6 over 12, or 1/2. And in fact, sine of 30 is 1/2. So this allows you to sort of, do some calculations a little bit quicker without using trig. Trig allows you to extend it, but this is just sort of the base model. Alrighty, I'll see you in class.